Alright, here's the next installment of Gower School Algebra 1, transforming graphs. This one's going to be about stretching and shrinking graphs, so we're going to think about what they're going to look like and what's going to happen to the equation when we stretch or shrink them. And I'm only talking in the vertical direction, so stretching and shrinking up and down, we're not going to affect the width side to side at all. It's not that you can't, but it requires kind of a different technique. And so since we're looking at functions that are one-to-one input and output, we're only going to be affecting the output but not the input. Okay, so we're not going to be adding or subtracting like we did to translate the graphs or slide the entire thing up and down and side to side, but instead we're going to multiply, which is going to make everything bigger by a certain factor. So if we multiply by a number larger than 1, everything is going to get farther away or stretched out. If we multiply by a number between 0 and 1, like a fraction, like 1/2 or 1/3, then the height of all the points is going to get decreased, which will effectively shrink the graph and make it smaller. So all this technique requires you to have your formula in the kind of standard form where it's y equals some function of x. It could be parabola with x squared, it could be a straight line, mx plus b, or it could even be a more complicated graph. But all these require you to start with y equals and then your formula. So to stretch it out, it's just what I said. You're going to multiply the entire right-hand side, so that's why it's important that you solve for y first. You're going to multiply the entire function on the right-hand side by whatever number bigger than 1. So if you multiply by 2, you're stretching by a factor of 2 or making it twice as big. If you multiply it by 10, you're stretching by a factor of 10, everything will be 10 times as big, etc. And to shrink it, you're going to multiply the entire right-hand side by a number smaller than 1, but bigger than 0. Because if you multiply by a negative, that will actually flip it upside down or reflect it, which we learned about in the previous section. But bigger than 0. So a positive number less than 1. Alternatively, instead of thinking of it as multiplying by like a fraction, you could think about it as dividing. So dividing by 3 will shrink everything by a factor of 3, and dividing by 3 is the same as multiplying by 1/3. So whichever way you like to think about it better is fine. And again, just to reiterate, we're only stretching or shrinking in the vertical direction. So we'll be affecting the output or height values, but we're not changing the width values at all. When you do this, though, a lot of times it looks like things got shrunken skinnier or they got stretched out. So let me give you an example. If you have a smiley face with a certain size to it, like this, for example, if you stretch this guy vertically, he might end up something like this. And then, it's going to be tough to draw. Okay, and so when you look at that, it seems kind of like it got squashed inward. But in effect, what happened is if you look at the distance from this side to this side, if I've drawn it well, it's the same as the distance from this side to this side. So the actual width of the shape or graph or whatever you have is not changing. It's only getting stretched out this way or shrunken down and scrunched this way. So the vertical height will be changing, but the horizontal part will not be changing. Okay, let's do a couple of examples. Again, we'll do a straight line and a parabola. Let's do y equals 6x plus 3, and we'll shrink by a factor of, I guess let's do by a factor of 3. That'll make it easy. So to shrink by a factor of 3, we're going to multiply by 1/3. So this is our old equation. Remember, it's good to label old and new. Our new equation is going to be y equals 1/3 times 6x plus 3. Okay, which is y equals 1/3 times 6 is 2x, and 1/3 times 3 is 1, so 2x plus 1. That's our new equation. Alright, so let's graph both the old and the new and see how they change. 6x plus 3 will start here at positive 3, and our slope is 6, so up 1, 2, 3, 4, 5, 6 over 1 puts us something like that, and then down 6, 2, 3, 4, 5, 6, backwards 1. 1, 2, 3, 4, 5, 6. So something very, very steep here. We're going through here, and we're going kind of down this way. So I know it's not the straightest of lines, but I've done as best I can with the mouse. Our new equation is 2x plus, this was a 1, 2x plus 1. So our new intercept is here, and our slope is 2. So up 2 over 1, up 2 over 1, up 2 over 1, down 2, backwards 1, down 2, backwards 1, down 2, backwards 1. So I can try to draw this line in, going through here. Okay, and so when you look at this at first, at least in my opinion, instead of looking like it got shrunk, it actually looks like it got tilted a little bit to the side. And so, I mean, arguably, that is arguably what happened. When we do a parabola, you'll be able to see that it's not actually tilting, it is shrinking, but the effect on a straight line is sometimes hard to see. But let's pick a couple of points to use as examples. This point right here is up at a height of 9. It moved down to a height of 3. So it was at 9, now it's at 3, which means it's 1/3 as high. Let's look at the y-intercept. It started at 3, it moved down to 1. So again, by a factor of 3 times smaller. This point where they cross is right on the x-axis. Similar to reflections, if you're on the x-axis and you reflect, you have nowhere to go. If you're on the x-axis, your height is 0. So if you stretch or shrink 0, it's going to stay at 0. So when you stretch or shrink graphs, they will cross on the x-axis. You should write that down. These will cross on the x-axis. That's not important to be able to solve them, but is a really good way to check and make sure you're doing it correctly. This point here used to be at -3, and it's shrunk down, and now it's only at -1, etc. So I think this illustration shows that if you scrunch it down, all the points individually make sense and match up with what we've done to the equation. All right, let's take a parabola, as we do a linear and a parabola to see the different cases. Let's do y equals x squared minus 1, and we'll stretch by a factor of 4. Okay, so our new equation is going, that's old, label that. Oh, I've failed to label these graphs. I've made a mistake. Let me go back to this one. We need to label this one as the new one, and this one as the old one. It's always important to label what your graphs are, and we should probably label this as a 1, a 2, a 3. I can't stress enough how important it is to label everything, both the axis and the old versus new, so that you can make sure that your equations match up with what you're graphing, and that way you can demonstrate both to me and to yourself that you really understand what you're doing. And if you look back on it later, it'll be a lot easier to see what you did and make sense of it. Okay, so back over here. So that's our old one. Y equals x squared minus 1, and we're going to stretch by a factor of 4. So our new equation, if I just multiply that by 4, I'll get y equals 4x squared minus 4. Okay, so on this one, I'm going to count by ones on the vertical axis, but on the horizontal axis, I'm going to actually count 3. 3 squares is going to represent 1 unit, and you'll see why in just a second. So there's -1, and there's -2. So this first one, x squared minus 1, it starts off at -1, so we start off at -1. We go over 1, up 1. Okay, over 1 is all the way over to here, and then up 1 is right there. Over 2 is all the way to here, up 4. 1, 2, 3, 4. Okay, backward 1, up 1 puts us here. Backward 2, up 4 puts us right here. And so this is going to give us a parabola that looks like this. So it doesn't look the same as the other ones that we had as our base parabola. It looks kind of more open or squashed out. And that's because on this axis I've counted 3 squares as 1 unit. The reason I've done that is so that the second one that we draw that's been stretched out won't just look like a straight line because it's so skinny. Okay, so let's draw this one. Y equals 4x squared minus 4. It has a starting value of -4, so we come down and we start right here at -4. Now we're going to go, normally you would have gone over 1, up 1, but it's been stretched by a factor of 4. So this 4 here in the numerator, right here is the coefficient of the x squared, tells you to go 4 times higher than you would have gone. So from here, we would normally go over 1, up 1, but instead we're going to go over 1, so that distance, 3 squares, right, is over 1, up 1, 2, 3, 4. So this point actually got used again. Then we're going to go over 2. We normally would have gone up 4, right? Let me draw these in. You would normally go over 1, up 1. And you would normally go over 2, up 4. But because we're stretching it by a factor of 4, we're not going to do that. We're going to go over 1, up 4, because it's 4 times higher. And instead of going like that, we're going to go over 2. We would have gone up 4. 4 times 4 is up 16. We're going to go up 16. So from here we have to go up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, something like that, really, really high. So we got this point and we got this point, so it's going to go parabolic and way up here. Likewise, we're going to go back 1, up 4, and then from the vertex back to up 16, and I'll just estimate it's around there. So this side is going to curve up like that. So this point right here got moved up 4 times higher. This point stayed where it was, again because it's on the axis and the graphs are going to cross on the axis. This point got moved 4 times lower. This point stayed on the axis, and this point got moved 4 times higher. And those are just the points that we use to graph it. But you can this idea works for anything. Let's pick this point right here. It was at 1. Now it's around 4. This point was around maybe a half or something, and now it's around 2. So my graph's not perfect, obviously, because I'm drawing with the mouse. But if you could draw a nice perfect parabola, you would see that every individual point is 4 times stretched out farther away from the axis. Alright, that's it for stretching and shrinking. You just have to remember to first solve the equation for y, and then multiply the entire right-hand side by something larger or smaller, and remember that your graph should always cross on the x-axis to confirm that you've done it correctly.